March the 9th, 1943. The cold North Atlantic swallowed another German U-boat without explanation, its crew of 48 men joining the growing list of submariners who simply vanished into the depths. Admiral Karl Dennett stood in his command bunker in Paris, staring at the operational map with mounting fury and confusion. Red pins marked the last known positions of his lost submarine 17 in the past 2 months alone. The pattern made no sense. His wolf packs were being hunted with impossible precision, intercepted in waters where no Allied vessel should have known to look. The mathematics of war had turned against Germany's undersea fleet, and Dennett could not understand why. His U-boats were the apex predators of the Atlantic, designed to strike from the shadows and disappear before enemy warships could respond. Yet somehow, British and American aircraft were finding them in conditions that should have made detection impossible at night, in fog, through storm clouds that reduced visibility to nothing. The submarines would surface to charge their batteries or ventilate their diesel-choked compartments, following procedures that had proven safe for years. Then, from nowhere, depth charges would rain down, or machine gun fire would rake their decks before they could dive to safety. Captain Heinrich Timm reported the most disturbing account from U-100-and-50-6. His boat had surfaced in complete darkness, 20 miles from the nearest convoy, with lookouts posted and listening equipment detecting no approaching vessels. Within 8 minutes, a British Wellington bomber appeared overhead, its searchlight stabbing through the night with supernatural accuracy. Tim crashed off his boat, but 3 depth charges detonated close enough to crack gauges and knock men from their stations. He escaped, barely, by diving to crushing depths that pushed his submarine's hull to its absolute limits. Similar stories filtered back from other commanders who survived their encounters. U-boats were being caught during the Black Gap, that vast mid-Atlantic region beyond the range of land-based aircraft where submarines had once operated with relative impunity. The Allies had somehow closed this gap, deploying long-range aircraft that hunted with relentless efficiency. Dennett's staff officers suggested various theories: improved hydrophones, infrared detection devices, or perhaps British spies within the Kriegsmarine reporting U-boat positions. None of these explanations satisfied the Admiral. The attacks showed too much precision, too much consistency. The losses were destroying Germany's Atlantic campaign. By March of 1943, Dennett needed his U-boats to sink 700,000 tons of Allied shipping, monthly to strangle Britain's supply lines. Instead, his submarines were being destroyed faster than shipyards could replace them. The hunters had become the hunted, and the German Naval Command had no idea how the Allies were accomplishing this reversal. Then, on a routine patrol along the French coast, everything changed. A German destroyer intercepted a damaged British bomber struggling back to England after a raid. The aircraft ditched in the channel, and German sailors pulled the crew from the freezing water before their plane sank. In the bomber's wreckage, recovery teams found something that made no sense: a strange electronic device mounted in the aircraft's belly, unlike any radar equipment German engineers had seen. It was compact, sophisticated, and operating on a wavelength that should have been impossible to generate. The device was carefully extracted from the wreckage and rushed to Naval Intelligence Headquarters in Paris, where Germany's finest technical minds would finally understand the invisible enemy that had been slaughtering their submarine fleet. March the 15th, 1943. The captured device arrived at the Kriegsmarine's Technical Research Facility in a wooden crate marked with red confidential stamps. Professor Walter Barth, Germany's leading radar expert, removed the equipment with the careful reverence of an archaeologist unearthing an ancient artifact. What he saw made him doubt his own expertise. The device was smaller than German radar units by half, elegantly designed, and built around a mysterious component that resembled a copper tube with internal cavities. Barth had never seen anything like it, and that terrified him more than the strategic implications. German radar technology operated on wavelengths between 1 and 2 meters, frequencies that provided decent detection ranges but lacked precision. The Kriegsmarine had assumed the Allies faced the same technical limitations. Every nation's physicists had concluded that generating shorter wavelength centimeter band frequencies would require prohibitively large and complex equipment unsuitable for aircraft. Barth himself had written papers explaining why such miniaturization was theoretically impossible. With current vacuum tube technology, the device sitting on his examination table proved all those assumptions catastrophically wrong. He carefully disassembled the unit, photographing each component and taking meticulous measurements. At the device's heart sat the mysterious copper tube, what British engineers called a cavity magnetron. Barth rotated it under laboratory lights, examining the precision machine cavities inside. The engineering was breathtaking, representing a quantum leap beyond anything German researchers had achieved. This single component could generate centimeter wavelength microwaves with extraordinary power and efficiency, enabling radar that could detect a submarine's conning tower from miles away, even in complete darkness or heavy weather. The implications crashed over Barth like a physical wave. Centimeter band radar explained everything: the impossible accuracy of Allied attacks, the nighttime intercepts, the devastating losses in the mid-Atlantic. A U-boat's metal hull would reflect these short wavelengths brilliantly, making the submarine visible to aircraft radar from distances that gave commanders no time to dive. The technology transformed every Allied patrol aircraft into a precision hunter, capable of detecting surface U-boats through clouds, fog, or the darkest nights. Germany's submarines had been fighting with Stone Age weapons against an enemy wielding laser-guided rifles. According to historical records maintained by the Royal Air Force Coastal Command, as documented in the official British naval histories, the cavity magnetron had been operational since early 1942. The British had mounted these new radar sets in Leland-equipped Wellingtons, creating hunter-killer aircraft that could patrol for hours, their radar scanning the ocean surface with unprecedented resolution. When the radar detected a submarine, the aircraft would approach silently before illuminating the target with powerful searchlights and attacking with depth charges before the U-boat crew could react. The Germans had been dying for over a year without understanding why. Barth drafted his report with hands that trembled slightly, choosing each word carefully because he knew the fury his conclusions would provoke. The Allies possessed a technology Germany could not match, deployed on a scale that suggested industrial capacity far beyond German capabilities. Worse, the cavity magnetron represented fundamental physics breakthroughs that German scientists had missed entirely. Britain and America weren't just ahead in the technology race. They were playing a different game altogether, with rules Germany didn't understand. He included technical drawings of the magnetron, measurements of its operating frequency, and calculations showing how centimeter band radar could detect submarine conning towers from distances up to 12 miles in ideal conditions. His report concluded with a grim assessment. Every German U-boat surfacing within range of Allied aircraft equipped with this technology was effectively committing suicide. The wolf packs that had terrorized the Atlantic were now being systematically exterminated by an enemy that could see in the dark. Admiral Dennis received Barth's report on March the 21st. He read it twice, then summoned his senior staff officers for an emergency conference. The document in his hands explained the unexplainable, but its conclusions demanded a complete strategic reassessment of Germany's naval war. March the 22nd, 1943. The conference room in Dennis's Paris headquarters felt more like a funeral parlor than a strategic planning center. Senior U-boat commanders sat in heavy silence as Barth presented his findings, using technical diagrams that might as well have been obituaries. Captain Hermann Rasch, who had lost his brother when U-391 disappeared without a trace, stared at the cavity magnetron schematic with barely controlled rage. The device looked innocent enough on paper, just copper and cavities, but it had turned the Atlantic Ocean into a killing field. Dennis listened to Barth's presentation with the stoic expression of a man watching his life's work collapse. He had pioneered the Wolfpack tactics that nearly starved Britain in 1940. In 1941, coordinating groups of submarines to overwhelm convoy defenses through sheer numbers and coordinated attacks. Those tactics assumed submarines could surface undetected, maneuver into attack positions, and escape before enemy forces responded. The cavity magnetron destroyed every assumption underlying German submarine warfare. Commander Werner Henk recently returned from a patrol where he barely escaped 3 separate aircraft attacks, raised the question everyone feared asking: if Allied aircraft could detect surface submarines from such distances, could U-boats operate at all? The mathematics were brutal. A submarine traveling on the surface could make 17 knots, allowing it to intercept convoys and reach distant patrol areas efficiently. Submerged, that same boat crawled at 7 knots, burning battery power that required surfacing to recharge. A U-boat that couldn't surface was essentially useless to slow the hunt, unable to recharge, and vulnerable to battery depletion that would force it to the surface anyway. Barth presented intercept logs that painted an even darker picture. British Coastal Command had increased aircraft patrols across the entire North Atlantic, with particular concentration in the Bay of Biscay, where U-boats transited to and from their French bases. The aircraft could loiter for hours, their radar sweeping vast areas of ocean, creating overlapping zones of detection that made surface transit suicidally dangerous. U-boats were being caught during their most vulnerable moments, when entering or leaving port, when approaching convoy routes, when recharging batteries after long submerged periods. The casualty statistics told their own horror story. In February of 1943, Allied forces sank 19 U-boats. March was tracking even worse, with 12 already lost and the month not yet finished. These weren't just numbers, they were entire crews, trained submariners who took 2 years to replace, expensive boats that required 6 months to build. Germany was losing the production race badly. British and American shipyards launched merchant vessels far faster than U-boats could sink them, while German shipyards couldn't replace submarine losses quickly enough to maintain fleet strength. Dönitz faced an impossible choice. He could continue current operations, accepting catastrophic losses in hope of sinking enough merchant ships to matter strategically, or he could withdraw the U-boat fleet from the Atlantic, conceding defeat in the Battle of the Atlantic and abandoning Germany's only effective weapon against Allied logistics. Neither option offered victory, only different flavors of failure. The British had achieved with one technological breakthrough what millions of tons of depth charges and escort vessels couldn't accomplish. They had broken the back of Germany's submarine fleet. Captain Klaus Schultz, who commanded the 9th U-boat flotilla, made a desperate suggestion. Perhaps German scientists could replicate the cavity magnetron, building their own centimeter-band radar to detect Allied aircraft before those aircraft detected submarines. Barth crushed that hope immediately. The British device represented years of research and industrial development. German laboratories understood the basic physics now, but creating working prototypes would take months. Manufacturing them in sufficient quantities for the entire U-boat fleet would take years Germany didn't have. The Kriegsmarine was fighting with obsolete technology against an enemy that had lapped them in the innovation race. The meeting adjourned without clear decisions, only grim acknowledgments of reality. Germany's U-boats would keep fighting because withdrawal meant certain defeat, but continued operations meant certain death for the men who crewed those submarines. It was mathematics written in blood, and every man in that room understood the equation perfectly. April the 3rd, 1943, when Commander James Thompson guided his Wellington bomber through thick cloud cover over the Bay of Biscay, his eyes fixed on the green glow of the radar scope mounted beside his seat. The device hummed softly, its cathode ray tube displaying a circular map of the ocean below. Most of the screen showed only electronic noise, the natural clutter of waves and weather, but Thompson watched for the distinct bright blip that indicated a surface submarine. He had been hunting U-boats for 11 months with this equipment, and the technology had transformed him from a frustrated patrol pilot into one of Britain's most effective submarine hunters. His radar operator, Sergeant Donald Matthews, adjusted the equipment's sensitivity while monitoring for contact. They had been airborne for 3 hours, part of the relentless patrol schedule that Coastal Command maintained across the U-boat transit routes. The Wellington carried depth charges in its bomb bay, a powerful Leylight searchlight for target illumination, and enough fuel for 9-hour patrols. Before the cavity magnetron radar, such patrols found submarines through luck and keen eyesight. Now, the radar's electronic gaze swept a circular area 20 miles in diameter, detecting metal targets that human eyes would never spot. Matthews suddenly straightened in his seat. Contact, bearing 270 degrees, range 8 miles. The blip on his scope was unmistakable, a solid return indicating a large metal object on the ocean surface. Thompson banked the Wellington toward the contact while his crew prepared for attack. The submarine crew had no idea death was approaching from above the clouds. The U-boat's lookouts would be scanning the sky and horizon, but the Wellington flew at 3,000 feet above solid overcast. The Germans couldn't see what they couldn't hear, and the aircraft's engines were too distant to detect over wind and wave noise. Thompson descended through the cloud layer at precisely calculated intervals, using the radar to guide his approach. At 2 miles, he could see the U-boat's silhouette on the choppy gray sea, a Type 7C submarine running on the surface at high speed, probably racing to reach its assigned patrol area. The submarine's lookouts still hadn't spotted the approaching bomber. Thompson aligned his attack run with practiced precision. The months of hunting compressed into these critical seconds. At half a mile, he activated the lee light, and 2 million candle power of blazing illumination stabbed down from the Wellington's belly. The effect was instantaneous. The submarine's deck crew scattered in panic, and the boat began a crash dive, its bow tilting down sharply as the captain ordered emergency submergence. But submarines couldn't dive instantly. The process took 45 seconds under ideal conditions, and the U-boat was caught completely exposed. Thompson's bombardier released for depth charges in a precise stick pattern, the weapons tumbling toward the churning water, where the submarine's stern was just disappearing. The charges were set to detonate at 50 feet depth, calculated to catch a diving submarine before it could reach safety. The explosion sent massive columns of water skyward, and Thompson circled to assess the damage. An oil slick spread across the surface, along with debris and what looked like pieces of equipment blown from the submarine's hull. The U-boat didn't resurface. Thompson's radio operator sent the contact report back to headquarters. One submarine destroyed, positioned 48 degrees north, 7 degrees west. It was his 14th confirmed U-boat kill, each one achieved through the same combination of radar detection, surprise approach, and devastating attack that the German admirals were only now beginning to understand. According to operational records from the Royal Air Force, as preserved in the British National Archives Coastal Command aircraft equipped with cavity, magnetron radar destroyed 36 U-boats in the first 4 months of 1943. The technology's impact extended beyond direct kills. U-boats forced to remain submerged couldn't reach their patrol areas quickly, couldn't chase convoys, couldn't effectively hunt merchant shipping. The submarine fleet's operational effectiveness collapsed, even faster than the kill statistics suggested. Thompson flew his Wellington back to base, already planning his next patrol. Below him, U-300 Dan-14 settled to the bottom of the Bay of Biscay, its crew of 4 to 7 men trapped inside the ruptured hull. They had never seen the aircraft that killed them, never heard its engines over the wind, never had a chance to fight back. The cavity magnetron had turned submarine warfare into a one-sided slaughter, and every U-boat commander now understood they were swimming in seas that offered no cover and no escape. April the 20th, 1943. Admiral Dennis stood before a map table at his headquarters, studying proposals from his technical staff with the focused intensity of a man watching his strategic options evaporate. The cavity magnetron had forced him to accept an uncomfortable truth. Germany could not win the technological race, so it must find ways to survive until better countermeasures emerged. His engineers had developed several desperate measures, each addressing symptoms rather than causes, each bought with blood and industrial resources Germany could barely afford. The first countermeasure was purely procedural: increased anti-aircraft armament on U-boats. If submarines couldn't avoid detection, perhaps they could fight off attacking aircraft. Dennis ordered shipyards to install additional anti-aircraft guns on submarine decks, creating floating anti-aircraft platforms that could challenge attacking bombers. The modification added weight and reduced underwater speed, but it gave U-boat commanders the option to remain surfaced and fight rather than diving into a depth charge attack. Several boats had successfully driven off aircraft using these enhanced defenses, though the tactic worked only when lookouts spotted approaching planes before the aircraft reached attack position. Commander Peter Kramer demonstrated the tactic's effectiveness when his U-3-100- and -30-3 encountered a British Liberator bomber over the Bay of Biscay. Rather than diving, Kramer ordered his gun crews to battle stations and engaged the aircraft with every weapon his boat carried. The surprised bomber crew found themselves flying into a wall of flak, taking hits that damaged their engines and forced them to abort the attack. Kramer's boat survived, but 3 crew members died at their guns, and his submarine needed yard repairs to fix battle damage. Fighting back was possible, but it remained desperately dangerous. The second countermeasure addressed the radar threat directly. German scientists, having examined the captured cavity magnetron, understood they couldn't replicate the technology quickly, but they could detect when enemy radar was scanning their submarines. Engineers developed a receiver called METOX that could detect centimeter-band radar transmissions, giving U-boat crews warning when Allied aircraft were hunting them. The device was crude: a simple receiver connected to a wooden frame antenna called the Biscay Cross, but it worked. U-boats equipped with METOX could detect radar emissions before the aircraft's radar got a solid return from the submarine, providing precious minutes to dive and escape. Dennis ordered METOX receivers installed on every operational U-boat by May of 1943. The device represented desperation engineering at its finest: not elegant, not sophisticated, just barely adequate to buy submarines a fighting chance. U-boat commanders reported that METOX warnings allowed them to crash dive before aircraft reached visual range, avoiding attacks that would otherwise have been impossible to evade. Survival rates improved slightly, though Allied pilots quickly noticed U-boats were diving earlier and adjusted their tactics accordingly. The third countermeasure was strategic rather than technical. Dennett studied patrol patterns and identified areas where Allied air coverage was thinnest. He redirected U-boats to these less patrolled regions, accepting longer transit times and reduced operational efficiency to avoid the meat grinder of the Bay of Biscay and Mid-Atlantic air gaps. Some boats were sent to distant waters of the Caribbean, the West African coast, the Indian Ocean where Allied aircraft patrols remained sparse. These deployments reduced pressure on the Atlantic convoy routes, but kept the U-boat fleet operational and inflicting losses on Allied shipping. Captain Eric Topp, one of Germany's most successful U-boat commanders, argued for an even more radical approach, abandoned traditional submarine warfare entirely, and developed true submersibles boats capable of remaining underwater for extended periods, never surfacing except in port. He proposed hydrogen peroxide-powered submarines that could generate power underwater, without consuming battery reserves. The concept was brilliant, but years away from practical implementation. Germany's scientists were working on such vessels, designated Type 21, but engineering challenges and industrial limitations meant they wouldn't enter service until late 1944 at the earliest. Historical records from the German Naval War Staff analyzed extensively in post-war studies show that these countermeasures produced mixed results. U-boat losses declined slightly in May and June of 1943, but remained catastrophically high compared to pre-radar months. More importantly, the effectiveness of Germany's submarine fleet plummeted. U-boats that spent most of their time submerged or operating in distant waters sank far fewer merchant ships. The Allied shipping tonnage losses dropped dramatically, falling below levels needed to impact Britain's war effort meaningfully. Dennett faced the bitter mathematics of attrition warfare. His countermeasures kept some U-boats alive longer, but they couldn't restore the operational advantages submarines had enjoyed before cavity magnetron radar deployment. The Battle of the Atlantic had fundamentally changed, and Germany lacked the technological or industrial capacity to change it back. The Admiral, who had nearly strangled Britain through submarine warfare, now watched his weapon become obsolete, rendered impotent by a device small enough to fit in a wooden crate. May the 24th, 1943, Admiral Dennett sat alone in his office long after his staff had departed for the evening, reading casualty reports that documented the death of his submarine force. May had become the bloodiest month in U-boat history. 41 submarines lost in 31 days. Their crews vanished into the Atlantic depths, their sacrifice achieving virtually nothing. The convoy battles that month resulted in catastrophic German defeats. Convoy Onslow 5 had been attacked by 15 U-boats and lost only 6 merchant ships while destroying 5 submarines and damaging 3 others so badly they had to abort patrols and limp back to France. The exchange rate was unsustainable, unwinnable, and utterly devastating. The fundamental calculus of submarine warfare had inverted. Before cavity magnetron radar, U-boats hunted convoys with relative safety, sinking ships faster than Allied shipyards could replace them while suffering acceptable losses. Now, submarines approached convoys under escort by air and sea forces that could detect them instantly, attack with overwhelming firepower, and coordinate responses that left U-boats with no escape routes. The hunters had become the hunted, and the prey was winning decisively. Commander Werner Hank returned from patrol with U-515 barely seaworthy, its pressure hull cracked by depth charges, to crew members dead, and nothing to show for 37 days at sea. He reported being attacked 7 times by aircraft once while submerged, when a British Liberator detected his periscope wake and attacked his estimated position with acoustic homing torpedoes, a new weapon that tracked submerged submarines by the noise of their propellers. German submarines faced threats from above, below, and in all directions. There was nowhere safe, nowhere to hide, no tactical advantage remaining. Dennett summoned his senior commanders for another conference, but this time the discussion wasn't about tactics or countermeasures. He needed to address the fundamental question: should Germany continue the Atlantic U-boat campaign at all? Captain Klaus Schultz argued for withdrawal, pointing out that the submarine force was being destroyed for no strategic gain. Germany's shipyards couldn't replace boats fast enough. The training pipeline couldn't replace crews quickly enough, and Allied merchant shipping losses had dropped to levels that didn't meaningfully impact Britain's war effort. Commander Adalbert Schnee presented the counter-argument. Withdrawing the U-boat fleet would free enormous Allied resources, aircraft, escort vessels, crews, industrial capacity for other purposes. Those resources would be redeployed to support the eventual invasion of Europe, making Germany's defensive task even more difficult. The submarine threat, even if much reduced, forced the Allies to maintain extensive anti-submarine warfare infrastructure. Every Allied destroyer hunting U-boats was a destroyer not bombarding German positions. Every patrol bomber scanning for submarines was a bomber not attacking German cities. The debate revealed the cruel trap Germany faced. Continuing the U-boat campaign meant accepting horrific casualties among submarine crews, while achieving minimal strategic results. Withdrawing meant conceding defeat in the Battle of the Atlantic and releasing Allied resources. For other operations against Germany, there were no good options, only different flavors of defeat, each bitter in its own way. Dönitz made his decision on May the 24th. He ordered the U-boat fleet to temporarily withdraw from the North Atlantic convoy routes, shifting operations to less defended areas while his staff worked to develop better countermeasures and tactics. The order shocked commanders who had fought in the Atlantic since the war's beginning. The ocean that Germany once dominated was now being abandoned to Allied control. British merchant ships would sail unmolested, American supplies would reach England without serious submarine threats, and the weapon that nearly won the war for Germany was being shelved like a broken tool. According to the official German Naval War Staff records extensively documented in post-war historical analyses, the May the 24th order marked the end of Germany's strategic submarine campaign. U-boats would continue operating for the remainder of the war, but never again would they pose an existential threat to Allied shipping. The cavity magnetron had not only defeated German submarines tactically, it had rendered them strategically irrelevant. One technological breakthrough, developed in British laboratories and deployed on Allied aircraft, had shifted the balance of naval warfare so dramatically that Germany's entire submarine strategy collapsed. The withdrawal order reached U-boat commanders at sea via encrypted radio messages. Boats already on patrol were recalled to base or redirected to distant waters. New patrols were canceled. The wolf packs that once terrorized the Atlantic were scattered, defeated not by superior tactics or overwhelming force, but by invisible centimeter wavelength radar beams that saw through darkness, clouds, and every attempt at concealment. The ocean that had been a hunting ground became a graveyard, and Germany's submariners understood they would never reclaim it. June 8, 1943. Professor Walther Barth stood in his Berlin laboratory examining a partially completed German copy of the British cavity magnetron. His engineers had been working around the clock since April, attempting to reverse engineer the captured device and develop domestic production capabilities. The results were frustrating. They understood the basic principles: the copper cavities, the magnetic fields, the resonance that generated microwaves, but translating that understanding into reliable manufacturing processes proved extraordinarily difficult. The British device represented not just clever physics, but also manufacturing precision that German industry struggled to replicate. The cavity magnetron seemed simple enough: a cylindrical copper block, with cavities machined into its interior, surrounded by a powerful magnet, with a cathode at its center. Electrons emitted from the cathode would spiral through the magnetic field, exciting electromagnetic oscillations in the cavities that produce microwaves at very high frequencies. The elegance was breathtaking, and the engineering challenges were enormous. The cavities needed to be machined to tolerances measured in hundredths of a millimeter. The magnetic field had to be precisely calibrated. The cathode materials had to withstand tremendous heat without degrading. British scientists at Birmingham University, working under Professors John Randall and Harry Boot, had solved these problems in 1940, creating the first practical cavity magnetron through brilliant innovation and relentless experimentation. Their breakthrough came from understanding that traditional vacuum tube designs couldn't generate the power and frequencies needed for effective short-wavelength radar. They needed something entirely new, a device that abandoned conventional wisdom about how microwave generators should work. The cavity magnetron represented lateral thinking at its finest, solving an impossible problem by changing the fundamental assumptions. Barth's team replicated a working prototype by May, but it performed inconsistently, generating less power than the British original and failing after several hours of operation. Manufacturing multiple units with consistent performance characteristics proved even more difficult. German factories lacked the specialized tools and quality control procedures that British and American industries had developed. Worse, Germany faced critical shortages of copper, tungsten, and other materials essential for magnetron construction. Even if Barth solved all the engineering challenges, German industry couldn't produce cavity magnetrons in the quantities needed to equip U-boats with competitive radar systems. The Americans had taken British cavity magnetron technology and industrialized it with terrifying efficiency. The Massachusetts Institute of Technology established the Radiation Laboratory in November 1940, where thousands of scientists and engineers worked to develop radar applications and manufacturing techniques. American factories were producing cavity magnetrons by the thousands, equipping not just patrol aircraft, but also ships, ground installations, and various experimental weapons. The Allied technological advantage wasn't just qualitative. It was quantitative on a scale Germany couldn't match. Barth Reed translated intelligence reports about American radar development with something approaching despair. The United States had converted entire industrial sectors to radar production, creating manufacturing capabilities that exceeded German capacity by orders of magnitude. Companies like Raytheon, General Electric, and Western Electric produced radar components using assembly line techniques that German craftsmanship-based manufacturing couldn't replicate. The Americans weren't just ahead technologically. They had created an entirely different approach to military production, treating advanced electronics like automobile parts that could be mass-produced with consistent quality. The technical revolution extended beyond the cavity magnetron itself. Allied scientists had developed increasingly sophisticated radar systems that could distinguish between different types of targets, track multiple objects simultaneously, and guide weapons onto targets with remarkable precision. British researchers created radar proximity fuses for anti-aircraft shells, turning every flak gun into a vastly more effective weapon. American scientists developed radar-guided bombs and missiles, creating weapons that could strike targets in darkness or bad weather. The cavity magnetron had opened doors to applications that transformed modern warfare in fundamental ways. According to post-war technical assessments compiled by Allied intelligence thoroughly documented in the Combined Intelligence Objectives Subcommittee reports, Germany never succeeded in mass-producing cavity magnetrons comparable to Allied devices. German radar technology remained stuck with longer wavelengths throughout the war, limiting effectiveness and leaving German forces at permanent disadvantage in electronic warfare. The technological gap that opened in 1942 never closed, and in some ways continued widening as Allied innovations accelerated. While German research struggled with material shortages and industrial limitations, Barth submitted his final report to the Naval War Staff in June of 1943. His conclusions were brutally honest. Germany could not replicate Allied radar capabilities during the war's remaining duration. The country lacked the industrial infrastructure, the specialized materials, the manufacturing expertise, and the scientific depth needed to close the gap. German U-boats would continue fighting with obsolete detection equipment against an enemy who could see them clearly from distances that made effective submarine operations nearly impossible. The Battle of the Atlantic was lost not on the ocean surface, but in physics laboratories and factory floors where Allied scientists and engineers had achieved breakthroughs that German research couldn't match. September 1st, 1945. The war in Europe had ended for months earlier, and Allied intelligence teams were systematically examining captured German military facilities, documenting the technological state of the defeated enemy. Commander James Thompson, now serving with the British Naval Intelligence Division, walked through a shuttered U-boat bunker in Lorient, France, examining the submarines that would never sail again. The massive concrete pen had sheltered dozens of U-boats during the war, protecting them from Allied bombing while they rearmed and repaired between patrols. Now it stood empty and silent, a monument to a failed strategy and obsolete technology. Thompson reflected on the strange trajectory of his wartime service. He had started as a frustrated patrol pilot, scanning empty ocean for submarines that remained invisible until they chose to reveal themselves through attacks on convoys. The cavity magnetron radar had transformed his effectiveness so dramatically that the change still felt almost miraculous. What had been a frustrating game of blind searching became a methodical hunt where technology gave him overwhelming advantages. The device that fit in a wooden crate had altered naval warfare more profoundly than any weapon system developed during the entire war. The statistical record told the story with brutal clarity. In 1942, before widespread cavity magnetron radar deployment, U-boats sank over 6 million tons of Allied shipping while losing 87 submarines. In 1943, after the technology reached operational deployment, U-boats sank less than 2 million tons while losing 244 submarines, nearly 3 times the loss rate for a quarter of the effectiveness. The mathematics represented thousands of merchant sailors who survived voyages that would have killed them a year earlier, and thousands of German submariners who died in a war their admirals could no longer win. The cavity magnetron's impact extended far beyond submarine warfare. The technology enabled radar systems that detected incoming aircraft from hundreds of miles away, giving Britain advance warning of German bombing raids. Shipboard radar guided naval gunfire with unprecedented accuracy, allowing destroyers to hit targets at night or in fog. Ground-based radar directed fighter aircraft to intercept enemy bombers, turning Britain's air defense from desperate improvisation into systematic protection. The device contributed to Allied victory in virtually every operational theater, from the Atlantic to the Pacific to the Mediterranean. Most remarkably, the cavity magnetron's peacetime applications would transform civilian life even more profoundly than it had transformed warfare. The same magnetron technology that detected submarines would eventually enable commercial radar for ship navigation and air traffic control. Medical researchers would develop magnetron-based equipment for cancer treatment. Communications companies would use magnetron principles for microwave relay towers that enabled long-distance telephone networks. Manufacturers would create microwave ovens using surplus military magnetrons, bringing cavity resonator technology into millions of homes for cooking food. Thompson examined a captured German radar set during his facility inspections, noting its bulky vacuum tubes and limited capabilities. The contrast with Allied equipment was striking. The Germans had fought the entire war with radar technology inferior to what Britain deployed in 1940. The consequences of that technological gap had been devastating for Germany's military and definitive for the war's outcome. Wars could be won or lost based on breakthroughs achieved in research laboratories, years before the shooting started, by scientists whose names remained largely unknown even after their innovations shaped history. According to comprehensive post-war analyses conducted by military historians extensively documented in official histories produced by both British and American naval commands, the Allied victory in the Battle of the Atlantic represented the most significant defeat of German military power during World War II. Losing control of the Atlantic meant Germany could not prevent Allied supplies from reaching Britain, could not isolate Britain economically, and could not prevent the eventual invasion of Europe. The cavity magnetron didn't win the war alone, but it defeated the weapon system that might have helped Germany achieve stalemate. If submarine warfare had remained effective, the German admirals who examined that captured radar said in March of 1943 had understood, in that moment, why their U-boats were vanishing. They saw the future clearly, a future where their submarines couldn't hide, couldn't hunt effectively, couldn't survive in waters they once dominated. Carl Dennis lived until 1980, long enough to see jet aircraft, nuclear submarines, and computers transform warfare yet again. He never forgot the moment when that small copper device revealed his fleet's doom, when technological surprise achieved what years of convoy battles and strategic planning couldn't accomplish. The complete defeat of Germany's submarine campaign. Thompson left the U-boat bunker and walked into the French sunlight, thinking about the crews who never returned from patrols, the merchant sailors who died in torpedo attacks, and the scientists who built the cavity magnetron without ever imagining how profoundly their invention would shape history. War's outcome often depended on invisible advantages, better logistics, superior production, and occasionally a single breakthrough that changed everything. The cavity magnetron was such a breakthrough, and the U-boat commanders who died without understanding why they were being hunted so effectively were victims of innovation as much as warfare. In the end, the Battle of the Atlantic was decided not by courage or tactics, but by wavelengths measured in centimeters and radar screens that revealed what darkness had always hidden.